Hi everyone, welcome back to Chem Help ASAP. Today we're going to be talking about equilibrium, but specifically we're going to be talking about heterogeneous equilibrium expressions. So let's get started. So what is heterogeneous equilibria, or what is a heterogeneous equilibrium? Well, a heterogeneous equilibrium occurs when one or more of the species in a reaction is a pure solid or a pure liquid. So when you're starting out with equilibrium, you usually deal with either everything in solution having a concentration, or you deal with all gases having a pressure. But that is not always the case for all reactions. So how do we handle this? Let's take a look at an example. So this is my balanced chemical equation, and you'll notice that my products are both gases, but my reactant is a solid. So initially, we would write a KEQ that looks like this, but of course, can you have a concentration of a solid? Of course, the answer is no, which means that the equilibrium constant is not dependent on the concentration of our ammonium chloride, or NH4Cl. So we do not include our pure solid, in this case our ammonium chloride, in our equilibrium expression. So our correct KEQ for this reaction is right here. I know it feels a little weird to say that the solid does not affect the equilibrium position, but experimentally, the amount of solid does not affect the equilibrium position. On the good side though, it does help simplify our equilibrium expressions, which can be very handy. So let's see some examples. Okay, so let's consider this reaction right here. We have some iron reacting with water to form iron oxide and hydrogen gas. So first we want to write the KEQ for this equation. Now initially, you might write the KEQ as so. It's just products over reactants, of course everything raised to their power. But we have some pure solids in this reaction. So this KEQ is not correct. We need to drop our iron oxide, and we also need to drop our iron. Those are both pure solids. Our KEQ simplifies to simply hydrogen gas over our water vapor. So at equilibrium, we have the concentration of hydrogen is 0.65 molar and water is 0.13. We need to calculate the KEQ for this equation. Taking our simplified expression, plugging in our numbers, raising everything to the fourth power, we get a KEQ of 625. Let's do one more example where we're dealing with pressures. Okay, so we have a new equation right here. We want to first write the Kp for this reaction. So initially, this is probably the Kp that you want to write, but this is not correct because we have some pure solids in this equation. We need to drop our UF4 and our UO2 and simplify our equation to this right here. So our Kp is only dependent on our water vapor and our pressure of our HF gas. So at equilibrium, the total pressure in the flask is 985 torr. If the pressure of our water is 357 torr, calculate Kp for this reaction. So we know that for our Kp, we simply need our water and our HF, but the problem only gives us the pressure of our water. How can we find the pressure of our HF? Well, we're going to use Dalton's law of partial pressures. So our total pressure is equal to the sum of the pressures of our water and our hydrofluoric acid. So I'm going to plug in what the problem gave me, my total pressure here, my pressure of water, so I can solve for my pressure of HF, and I get a pressure of 628 torr. Now I can plug in over here. So again, plugging in my water, plugging in my hydrofluoric acid, making sure I raise each of these to the proper power. I get a Kp of 8.19 times 10 to the negative 7th. So when you're working problems with Kp and pressures, just always be ready to potentially use Dalton's law of partial pressure as an added layer of complexity to the problem. I hope you found this video helpful, and thanks so much for watching.